I would like to talk about using the Hamiltonian and going over canonical transformations. The canonical transformations. So when we talk about canonical transformations, we talk about these canonical variables, position q and momentum p, and what would happen if we transform that into a frame of reference that was q bar, p bar. So what would happen to the Hamiltonian? And what we could do is we could say, well, we can derive the Hamiltonian in the variables q bar and p bar from the Legendre transformation of summing over the different components of p in the bar system times the velocity in the bar system, so the time derivative of the position minus the Lagrangian in the barred system, like this. So we could define the Hamiltonian that way. But what I want to talk about right now is basically finding a way to test whether or not q bar and p bar are going to be canonical variables, in that new frame of reference. Testing the q bar and the p bar with the Hamiltonian. So what I'm going to do is I'm going to start with looking at the derivative of my Hamiltonian with respect to the momentum in the unbarred system. So I'm going to call that the original frame of reference. So I'm looking at the ith component of the momentum and how the Hamiltonian changes with respect to that. Now that should be the same thing as the change in the Hamiltonian in the barred system, the transformed system, with respect to the original frame of reference. And so if we do that, I could now apply the chain rule and say that it's the sum over all components k of the Hamiltonian as it changes with the position in the barred frame of reference, the k component, and then times q bar k with respect to the momentum I in the original frame of reference. And then we have to do the same thing for the momentum variable. So I look at the change in the Hamiltonian with respect to the momentum in the transform frame of reference, sub k, and then the change in the momentum p bar sub k with respect to p sub I. So that's just expanding the Hamiltonian by the chain rule. And I could do the same thing for our position. I could take the derivative of the Hamiltonian in our original frame of reference with respect to position, qi, which could give me the same result with the Hamiltonian in the transformed system, q bar p bar, with respect to q. And if you work out the chain rule, you get something similar to above. Where now I'm just taking the derivative with respect to position in the non-transform, in the original frame of reference. And I don't want to forget the parentheses to show that I'm taking the sum over both terms. Okay, so I mean that's just operating with the chain rule. That's just some easy calculus. So now what I want to do is I want to make some substitutions. So let's take a look at the Poisson bracket. So if I look at the velocity in the barred system, sub j, so I'm using now component j, that's just the time derivative of the position in the barred system, which I can also write as the Poisson bracket of the position in the barred system with respect to the Hamiltonian. So I'm taking the Poisson bracket of the position and the Hamiltonian, and this can be the Hamiltonian in the barred system. And so now what I can do is to basically replace. Well, let me write out what the Poisson bracket looks like. It's the sum over, let's say, components I of the derivative of q bar dq and dh dp, and then minus, now if we rearrange the cyclic variables, then we have dq bar j with respect to momentum and dh dq, like so. So that's writing out the Poisson bracket. And now what I want to do is to substitute in. So come back up here and take my derivative, which I have right here, with respect to position, and put it in to this term right down here on the bottom. And then do the same thing with the derivative with respect of the Hamiltonian with respect to momentum, and to use the result way up top here, and substitute that in. So this is going to get kind of messy, but I'm going to do the substitution. And so what I have is q bar dot, the velocity in the barred frame of reference, sub j, is the sum of k and the sum of I. So the summing of the k components comes from the derivatives of the Hamiltonian. The summing over the I components comes from the Poisson bracket. And let's put it all together. So I've got dq bar dqi, and then we plug in the results from above, and I get the derivative of the Hamiltonian with respect to q bar sub k times the derivative of q bar sub k with respect to the momentum, plus the derivative of the Hamiltonian with respect to the momentum barred, and then the derivative of the momentum barred with respect to the momentum in the unbarred system. Okay. So I just made that first substitution minus the derivative q bar sub j over dp. And now I'll put in the results for that derivative of the Hamiltonian with respect to q, and I get the Hamiltonian with respect to q bar sub k, the derivative of q bar sub k with respect to position qi, plus the derivative of the Hamiltonian with respect to the momentum bar, and the derivative of the momentum barred with respect to position q. Okay. So now I have all these pieces, and what I can do is I can basically group terms. So why don't I group all the terms that are, so I'll do the sum of k and the sum of I, and I'll group all the terms that are the derivative of the Hamiltonian with respect to q bar. And what I get is, if I with respect to q bar, I get dq bar j dqi dq bar k with respect to the momentum plus, oh no, not plus, minus dq bar j dp I dq bar k dq I. So that's just grouping together the terms right here and the terms right here, and what that gives me is a Poisson bracket. So I can put in the next terms, so plus dh, the derivative of the Hamiltonian with respect to the momentum bar, and what I get is the dq bar j d qi dp bar k and dp I minus dq bar j dp I dp bar k over dq I. And all of that is summed over these two sums. So if I now look at it, if I take the sum over I, I've got the Poisson bracket of q bar and the Poisson bracket of q bar p bar. So it's getting kind of messy, but we can clean it up now, because what we have is the summation over the index k, and I've got dh over dq bar times the Poisson bracket of q bar j, q bar k, plus, I'll write it down here, the derivative of the Hamiltonian with respect to the momentum barred, and that's the Poisson bracket of q bar j, comma, p k. So I now have something a little more compact. Everything is written in terms of Poisson brackets. And if you remember the identity, the Poisson bracket of two positions is 0, and the Poisson bracket of the position and the momentum is the Kronecker delta. So in this case, it would be jk, right here. So that means I can now write the velocity in the barred system, sub j, is equal to the sum over the components k times the derivative of the Hamiltonian with respect to the momentum in the barred system times the Kronecker delta, jk, which basically leaves me with the derivative of the Hamiltonian with respect to the momentum in the barred system, which is one of Hamilton's relations. And so all of this was possible because I have these identities that the Poisson bracket right here of two positions is 0, and the Poisson bracket for a position and a momentum is the Kronecker delta. And so this is going to be now our condition. The other condition we could add to it, which we didn't work out here, is the Poisson bracket of the momentum, pj and pk, should also be 0. So these three conditions right here, the Poisson brackets, since they work in the unbarred system, the original frame of reference, and they give us the same result, they return the Hamilton's equation to us, then they also work in the barred system. So for two variables to be a canonical transformation, these Poisson bracket identities have to be satisfied.